All right, we are finally here. In this video, for the first time all term, we will actually be able to answer this basic question, this fundamental question of Calculus 2. Determine the area under some curve. You're like, no, we already did that. No. We've estimated the area under a curve already, but we've never actually determined it. We've never actually calculated that amount. Today, we'll be able to do that. And in order to be able to do that, we'll have to use all these different things that we learned in these previous videos. So you watched all these videos kind of picking apart these little techniques and tools that we'll end up using later, but it's really unsatisfying to watch all those videos. You're like, I don't get it. Like, I haven't used these yet. What are you making me watch these for? And it's really frustrating for a student. And then finally, in this video here, it all comes together, and it's somewhat satisfying, and it's a really important seminal point in Calculus 2, where we actually calculate the area underneath the curve. So we're going to do it. And the way we're going to do it is we're going to start out with the same formula we used before. Remember this picture here? We had a function and we wanted to estimate the area underneath the curve. So we drew these rectangles, and we can either use left endpoints or we can use right endpoints, and we can make as many rectangles as we want. There could just be 3 of them, there could be 4 of them, there could be more. And that kind of gives us these formulas here for left endpoints and right endpoints. What we're going to do is that same idea, except the rectangles we will be using will be infinitely thin. They'll be super duper duper thin, infinitely thin, so that the rectangles themselves can perfectly trace out the shape of the curve. And you're like, okay, we're using left endpoints or right endpoints. Well, guess what? It doesn't matter. Because if this rectangle in blue here is infinitely thin, its left endpoint is right next to its right endpoint. So it really doesn't matter whether you use this formula or this formula. For simplicity's sake, I'm always going to use this formula here. And the reason why is I like the index to go from 1 to n. It's easier than if it goes from 0 to n minus 1. And all the formulas that we've developed, our index has gone from 1 to n. So I'm going to copy this r sub n formula right here. As promised, here is that formula. And maybe you remember this formula. Maybe you're somewhat comfortable even using this formula at this point in the class. You can kind of see that each of these terms represent the area of a rectangle. Here's the width of the rectangle. Here's the height of the rectangle. It'd be awesome if you had that all together in your head at this point. And these weird looking symbols, we have formulas for those as well. And again, these formulas, sure, you can memorize them if you want, but I really would recommend understanding them. They're very intuitive, all 3 of these guys. And if you kind of understand them, it makes this section pretty easy. And if it's memorization, you can kind of get it, and then you immediately forget it the next week. So the idea here is delta x is just referring to the width of these rectangles. And so you can think about there's these really thin rectangles, but how wide are they? Well, it depends. How far are they trying to cover? Well, they cover from b minus a, whatever that is. Here's my point A, which is 0 in this case. And here's my point B, which is 1 in this case. So they have to span a total length of 1, b minus a. But each rectangle individually isn't that wide. It's all of them together that span that width. So what I want to do is figure out the total width that they all span and then divide by how many of them I have. That's my formula for delta x, is b minus a over n. The other formula is the xi formula, which maybe I can reference above. And when we're using right endpoints, which is what this picture denotes, xi just represents the height of the ith rectangle. And I know that sounds kind of weird, but all I'm saying is x1 here is the height of the first rectangle, because the first rectangle goes from x naught to x1, but since we're using right endpoints, it's x1 that matters. x2 represents the height of the second rectangle, x3 the height of the third rectangle, and so on. And how do you refer to those when you don't have a picture like this? Well, if you think about x3, for example, you can think about it's just a little ways away from x naught. X naught I always get for free. That's always a, which will be a value given in the problem. And so all I have to figure out is how far above a is x3. Well, x3 is going to be exactly 3 of these delta x's, right? The first delta x gets me to here. The second one gets me to here. The third one gets me to here. So x3, to get there, you just start out with a and add 3 of these delta x's. That's all this formula here is saying, just more generally speaking. If i's are all 3's, x3 is start out at a and then add 3, because the i's are all 3's, of these delta x's. And there's nothing special about x3. That works for all the different xi values. So these are the formulas that we will need in order to answer this question. Determine the area under this curve from x equals 0 to x equals 1. And I'm using the curve y equals x squared, but you don't have to. And I'm going from 0 to 1 to make things as easy as possible, but you don't have to. And in the next video, I'll relax all those assumptions and make things a little bit more complicated. All right, let's do it. Maybe a good way to start is to look at what's given to me in the problem. I'm going from x equals 0 to x equals 1. So that means that a is equal to 0 and b is equal to 1. And with that information, I can figure out what delta x is equal to. Delta x is always b minus a over n. and b is 1, and a is 0, so 1 minus 0 is just 1. And you're like, what is n? N is just n. Because I'm not going to figure out R3 or R4 or R5. I'm going to figure out Rn. I'm going to let myself have n rectangles. I'm not going to limit it to some finite number. And then I'm going to look at the limit when n approaches infinity. That'll make these infinitely skinny. Anyways, a and b gives me delta x. What about xi? Well, I can get that as well. Xi would just be a, whatever a is, 0 in this case, plus I times delta x. Well, delta x I just figured out above was 1 over n, so I get 0 plus I times 1 over n. Or if I want to simplify things a little bit, I could just say I got I over n. And you're like, oh, nice, xi is always just I over n? No, it only works out really nicely when a and b are 0 and 1 like they are here. In the next video, I'll show you how to deal with these things when the numbers aren't quite so nice. I have delta x and I have xi. I can use this formula. I could figure out Rn. R sub n is going to be the sum from I equals 1 up to n of delta x. Well, I don't need to write delta x because I know delta x is 1 over n. Times f of xi. Well, xi is I over n, so maybe I'll write this in 2 steps for you. F of xi would be f of I over n. Wait, what's f of I over n? Well, f of x is just x squared. So this is just saying take your function f of x equals x squared and change the inputs, the x's, into I over n. So this is going to be the sum from I equals 1 to n of 1 over n times I over n squared. Oh, you always square that? No, you do whatever the function is telling you to do. In this case, my function is f of x equals x squared, which is why this is squared. I get rid of this f by putting in this squared right here. That's what Rn is equal to. That's not quite what I want, but it's really, really close to what I want. What I want is the area under the curve from y equals x squared from x equals 0 to x equals 1. I need some shorthand. I need a nice way of writing that. Turns out there is such a way. Here's the shorthand. This mess of symbols right here means exactly this in English. This is asking you the question, how much area is there underneath the curve x squared, here's where the function is specified, from x equals 0 to x equals 1. And you're like, what's this little dx part? It's just a symbol for now. I mean, this whole thing is just one big symbol. And what you're supposed to do is be able to look at this symbol and translate this symbol into this question. If you're curious, the people who came up with this symbol, why they chose all this, well, the x squared is kind of referring to the height of the different rectangles, and the dx is kind of referring to the width, the delta x of the different rectangles. But up here, we're kind of assuming that these rectangles have a finite width and a given height, whereas down here, we're kind of considering more the infinite case because we want to know the exact area underneath the curve, not an estimation. So instead of delta x representing the width, we use this little dx symbol. And that might look familiar from Calculus 1. In Calculus 1, maybe you did stuff like dy over dx. And sometimes it was d's, and sometimes it was this made-up letter del, which is like a d without a line on it. Maybe you even saw it written as delta y over delta x. They all kind of sort of mean the same thing, written in different ways. For now, just think about this as a symbol that goes with this. Don't think about plugging in anything here. Later on, we'll have a more nuanced view of this. But for now, this is just the question. In fact, I can make this a formula for you. If I want to make it a formula, I should probably make it more generic. I shouldn't say it goes from 0 to 1. I should say it goes from a to b. And I shouldn't say that my function is x squared. I should just say it's f of x to keep things generic. And all this is equal to is this. It's just the limit as n approaches infinity of Rn. Right, where Rn is this thing that's defined up here. If you want to write the whole thing out, you can. There you go. Here's our formula. Here's our formula for the definite integral. Okay, take a step back here. Think about where you were like 2 weeks ago, assuming you've never seen Calc 2 before. If somebody had said, you're going to figure this thing out, and here's the formula for it. Like, this is another language. This is so intimidating. We have limits, infinite limits of these weird sigma things that we don't quite understand. And then this mess here. Like, this is really deep math that you're doing right here if you're able to figure out this problem. And if you just look at this page, if you handed this page to your roommate who's not in calculus, they'd be like, I'm never taking this class. It's going to be the worst thing ever. But it's really not that bad if you just take it one step at a time. This is just representing the same thing we've been doing, except the infinite case of it. right? This formula, when we derived it, we thought about a more finite case, length times the height of these different rectangles. It's the same idea down here. It's just now we're going to have infinitely many rectangles so that each rectangle kind of perfectly traces out the curve of whatever function we have. Okay, let's do it. The integral from 0 to 1 of x squared dx. Well, I have a formula for the integral from a to b of f of x dx. It's right here. And you could memorize that formula, or maybe you could just kind of understand what's going on. It's definitely going to be the limit as n approaches infinity of something. That something will be Rn, which you recall is the sum from I equals 1 to n of delta x f of xi. Above, I wrote that delta x is 1 over n, and I wrote that f of xi is I over n squared. If I could evaluate this limit, I'd be done. But how in the world are we going to do this? I mean, think about your knowledge of limits, going back to 2.5 and 4.5. I certainly couldn't ask you to do stuff with limits with n's and i's and all that in that section. Well, I think you know more than you think you know. Think about what this symbol right here is telling you. The only thing that is changing is I. This is a whole bunch of copies of this thing. Every copy looks the exact same, except the I changes. And the I goes from 1 to 2 to 3 to 4. And so I have a separate term for each of those until it gets up to n. And what is n? Well, later on, we're going to let n go to infinity, but don't worry about that for now. N is just kind of a placeholder. So it represents the number of terms that I'm going to have in this sum. Each of those terms will look very, very similar. The only thing that's changing is this I right here. Think about if you rewrote this. Can you see algebraically how this is the exact same as this? I over n squared is I squared over n squared. But then if I multiply 1 over n times I squared over n squared, I get I squared up on the top and n cubed down on the bottom, which if you really wanted to illustrate something for students, I suppose you could write this way, 1 over n cubed times I squared. If you could talk yourself into this and this being the same, even if you don't see why I'm writing them this way, if you can see that this and this is the same, you can make a huge jump. Because really all that's going on here is a constant times this I squared thing. The constant is 1 over n cubed, and I know n cubed feels like a variable, feels like it's changing, but it's not. It's something that is fixed. The only thing that changes in every one of these terms is the I, the index. So this is the exact same in every one of these terms. Why is that important? Remember this? Remember what happened when we were taking a sum of a constant times something that's changing? This x sub I, the only thing that was changing was the x sub I. We argued that sure, you could pull the constant out in front. That makes perfect sense because all this is saying is I'm adding up a whole bunch of terms and they all have the same c in them. So I could factor that c out in front. We're going to do that same thing, except the constant that we're factoring out in front is 1 over n cubed. So I can rewrite this as the limit as n approaches infinity of 1 over n cubed times the sum of I equals 1 to n of I squared. This is just a constant, no problem. Pull it out in front. Note, you don't want to put it in front of the limit because the limit you're taking involves this n, so we have to leave that here. But you can certainly pull it out in front of the sigma as we showed in that previous formula. All right, so I guess I can do that, but what about this part? What's the sum from I equals 1 to n of I squared? Like, what's this thing right here? How am I ever going to simplify that? Oh, wait. Remember your good friend Fallhaber here in these formulas? The sum from I equals 1 to n of I? Nope. The sum from I equals 1 to n of I squared? Aha. That's why you told me this weird thing. That's why you made that video that half of us didn't even watch showing how to prove this by induction. The sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. Let me add that to our growing list of formulas here in green that we referenced just to answer this question. The sum from I equals 1 to n of I squared is exactly what we have here. It's this stuff. So I can rewrite this line as this line. Right? Just change this part of it into this expression here. Like, wow, this is getting kind of wild. Like this page, again, think about this page without the context. This is pretty impressive what you can do. If you're following this at all, you should be really proud of yourself. We're still not done though. But we kind of are. In 2.5, I could give you this and you'd be all right with it. I know it's been a long time and maybe you don't remember this, but in 2.5, we did lots of limits involving infinity, where either the question involves infinity or the answer involved infinity. Let's focus on that first type now. And we looked at lots of cases where we were trying to figure out, let's see, here's one. The limit as x, we use the letter x instead of the letter n, who cares? Approaches negative infinity, positive infinity. We did both. We were good with these. Of a polynomial divided by a polynomial. That's what you have. Right? Instead of using the letter x, I'm using the letter n, but that doesn't matter. That's the variable that you see floating around in here if you want to think about it in terms of a rational function. It's just a polynomial over polynomial. Figure out this limit and you're done. How do you want me to figure out this limit? I don't care. You do it however you want to do it. You like L'Hopital? Do your L'Hopital thing. Realize that this is an infinity over infinity case and take a derivative. You'll still have infinity over infinity. Do it again, do it again. Think 3 or 4 times, you'll be done, and you'll get your answer. What I typically do is you start to see some patterns in here, right? If I were to expand out I'll do it for you. I'm going to expand out this polynomial up top. I'm going to do n plus 1 times 2n plus 1 to get 2n squared plus 3n plus 1. That's just basic FOIL up here up on the top. And I'm going to take this n and distribute it through, and I'm going to take this n cubed and distribute it through. And that's going to get me here. And then, I don't know, I guess you can do the thing where you pretend that you're going to divide each of these terms by n cubed. Remember when you did that? And that makes this a 2 and this a 6, and this 3 over n, and this 1 over n squared. But when n approaches infinity, the 3 over n and the 1 over n squared just go away, and you're left with just 2 over 6. Maybe you can get to the point where you can just recognize, let me write it in 2 steps, just in case it helps anybody, that this limit is just a third. And then when you get really good at that, you won't even expand out these polynomials. You'll go back to this step and be like, well, if I were to expand them out, the n times the 2n would give me 2n cubed, and everything else would be a smaller degree, so I don't care about it. On the bottom, I got 6n cubed. So 2n cubed over 6n cubed, that's the same as 2 over 6, which is 1 over 3. You'll soon be able to go straight from this line to this line. But you evaluate the limits however you want to evaluate the limits. I'm not super worried about that. You proved to me that you could do that in 2.5. What I want you to see are all the steps to get us there. And I want you to appreciate it, right? I mean, I wish we were in class together. I wish you could see me smiling right now. I wish I could pat you on the back as you solved one of these, because this is amazing math that you're doing if you can get through and solve one of these. The chain of logic that it takes to figure out this seemingly easy question is really, really intense. And if you're piecing it all together, if these aren't just symbols that are kind of memorized like flashcards, but they sort of make sense in terms of rectangles and stuff, that's really, really impressive. You have a concept, you are grasping a concept that most human beings will never grasp in their lifetime. Right? We're starting to get to that point. Calculus 2 is something that a lot of people, more than half the population, never, ever, ever understand. And if you followed this video, you understand arguably one of the more challenging concepts in Calculus 2, which is pretty nuts.